Hi, Professor. I had a question about the homework.
Sure. What's up?
Can I share my screen real quick?
Yes. Let me go ahead and stop this one. Okay, go for it.
Okay. All right. Can you see my answers?
Yes.
All right. I was doing the imperial units, and I looked up the scale at the bottom, and I noticed that my bridge is like it's small. It looks like it's 8 feet right now.
Yeah.
Is
It's
that?
it's a small bridge. Yeah. It's not a full size bridge at all.
Oh, okay. Okay.
Yeah.
Gotcha. Okay.
It's supposed to be like that. Yeah.
Okay. Um. So, what would like a loading scenario be for that? Is it like a toy or something?
Yeah. You can do that. It's not quite toy size, and so it's still 8 feet
Mhm.
long, and so maybe you can just take kind of the um, the maybe the weight of a car, maybe cut it in half. And so that's kind of what that's kind of the scaling that I use for mine. Yeah.
Okay, yeah, because like I saw like there's a beam at the top too. And it's only like 2 feet up there. Like,
Yeah.
yeah, so yeah, I was having a hard time thinking of like actual like scenarios.
Mhm.
Yeah. So
Yeah.
that's like
You
my
can
concern.
say it's I don't know, maybe like a car for a dwarf or something like that.
Oh, okay. Okay. Oh, thank you. Oh,
Yeah.
so, um, like I really don't know what because I wanted to do like a load of like winds acting on it, but I mean I guess it's slow to the ground, so you have like an idea of what a realistic like what the magnitude would be in that case?
Hmm. Yeah, so for the wind, you can input it as like a pressure, and so that's usually what people do. They put a pressure on one side of the bridge.
Mhm.
And so what's interesting about wind pressure is that a lot of it's dependent on speed. And so you could have, normally kind of the conventional wisdom is that if you have a bridge that's higher up, then you would have higher wind speeds. But you can have situations where you have a lower bridge and kind of a situation where your wind speeds can still be pretty high. And so, for example, if you have a bridge kind of at the bottom of a canyon, right? And so in a canyon, you kind of have this funneling effect where you have kind of a lot of wind coming in through there. And so you can still get some high speed there. And so you can still apply, pretty high pressures um, of, I don't know, what's a good one in PSI? I always think of wind pressures in terms of atmospheres, but I don't have that conversion in my head. So let's do 1 ATM to PSI. Maybe something on the order of like maybe 5 or 6 PSI, for kind of a normal windy day. Um, that might be something that's reasonable. Maybe going up to 10 PSI for that.
Oh, okay. Thank you. Thank you.
Mhm. Okay, it's 5:30. Let's go and get started. All right, good evening, everybody. How's everyone doing today? All right. First of all, thank you guys for meeting virtually. I'm recovering from my sickness, and so I should be able to come back on Thursday. But maybe I mentioned this to maybe some of you before, but I'm planning a wedding for the end of this semester. So having a couple of days at home to kind of sort things out has been really helpful. So thank you guys for your flexibility and meeting online for the past couple of days. But I will be back in class on Thursday. Okay. So the plan for today, so for the last couple classes, we've been going over we've introduced this idea of the direct stiffness method. And so, we kind of introduced this with the context that, this is a good representation in terms of, how the finite element method works, on a mathematical basis. Okay. And so we're going to continue that today. So we're going to introduce a new type of element called the truss element. And then we'll talk about kind of how that works, how that's factored in, and then we'll start our discussion of 2D analysis using direct stiffness. Okay. All right. So quite a lot to do today, and hopefully we'll get to a good point where we can pick it up on Thursday. Okay. Any questions on anything before we get started for today? Okay. All right. So let's go ahead and get started. Right? And so the topic for today is what I call truss equations. Okay. So like I mentioned before, that we've introduced this idea of the direct stiffness method, right? It's a good, it may not be exactly what ANSYS is running on the back end, but it shares a lot of similarities. And kind of the most important thing is that it kind of illustrates how finite elements or problems are set up from a mathematical or computational point of view. Okay. Okay. And so even though we're not going to be doing the kind of the hardcore calculations that are associated with solving these matrices, it's still important to kind of understand kind of how these problems are set up. Just so that you can, first of all, kind of get a good appreciation for what ANSYS is doing on the back end. But sometimes when you run into some errors in ANSYS, and so I know kind of a lot of people have run into the dreaded pivot warning or pivoting error. And so then you'll kind of know a bit better in terms of what's actually going on and why you're getting that error. Okay. Okay. And so today we're introducing a new element type. And so all we've done so far are spring elements. And so today we're going to introduce something called a truss element. Okay. Okay. Which basically is a structural element that's long and slender. Okay, and so it's kind of what we associate to be beams from before, but we assume that this member can only be either stretched or compressed in its axial direction. Okay. Right, and so its motion or kind of the deformation that a truss allows is actually exactly the same as a spring. So if you think about a spring, a spring also can only stretch and compress, in its axial direction, right? And so that's we assume that the springs can only kind of get longer or get shorter, right? And so truss elements are the same way. It's just that the physics is a little bit different. Okay. And so a truss element, usually the way that it's represented is it's represented as a long rod like this, okay? And we have to characterize this rod using its geometrical and material properties, okay? Okay. And so the list of properties that it has is, first of all, we have its Young's modulus, okay? Right, and so we call that E, and so that's a property we should be very familiar with because that represents the stiffness or the strength of the rod itself, okay? We have the length, the overall length of the rod, okay? We call that L. And number three, we have its cross-sectional area. and we call that A. And so the cross-sectional area is the area of the cross-section. Okay, and so we're going to assume that all of our truss elements have a uniform cross-section, so it's going to be the same cross-sectional area throughout. Okay. Okay, and so basically the idea here is, we're going to run through basically the same kind of logic, the same kind of progression that we did for the spring elements, except that we're going to be using truss elements instead. And so we're going to go through the same thing. So we're going to derive its element stiffness matrix. We're going to do some example problems with it where we do some assembly. We'll apply boundary conditions and then solve for our solution. Okay. Okay. So let's start with its element stiffness matrix. Okay. And so if you remember kind of from the process that we followed before, the element stiffness matrix is kind of core to the whole thing. Okay. Okay. All right. And so, just to kind of remind you, the element stiffness matrix represents the relationship between external forcings and the response of our structural member. Okay. All right. And so just like we did with the spring, I'm going to take our truss element here and kind of expose it to an equilibrium force. And so I'm going to apply a tensile force on both sides. Okay. Okay. So a tensile force T on both sides. Okay. And then also very similar to the spring, we're going to mark each side of the element here as a node. Okay. And so we're going to call this node 1 on the left, node 2 on the right. Okay. We can represent the deformation or the displacement of each node with a variable. Okay. Okay. So D1 and D2 there represent the displacement of the left node and the right node. As is shown. Okay. And then also for our element stiffness matrix, we also need to represent the forces acting on each node. Okay. Okay. So F1, F2 represent the forces that are being applied on the node on the left and the node on the right. Okay. Okay, so let me go ahead and write this down. So D1, D2. And then F1, F2. Okay. F1 and F2 are the forces being applied at the ends of the element. Okay. Okay. So let's see how we can use this framework. So the framework provided by D1 and D2, along with the external forces of T on both sides, and then see if we can get kind of an element stiffness matrix from this. Okay. All right. So first of all, let's make the observation. And so even though we've kind of made variables for this, we already know exactly how much force is being applied on each side, right? And so right away we can say that F1 is equal to minus T. Okay. because the way we define F1, F2, we define their positive directions going to the right. Okay. And so since the force on node 1 is being applied to the left, we're gonna say that that's equal to minus T. And F2 here is equal to T, okay? Because the force being applied on that node is a positive one, okay? So let's keep that in mind, and we'll kind of stash that away for later once we kind of have a force, force displacement relationship, okay? All right, and so if you recall, when we did this exercise for the spring, we had kind of an explicit relationship where we had force is equal to K times X, right? So we kind of had an equation built in which showed this relationship between force and displacement, right? And so that was our Hooke's law. So we don't have such a thing for our truss element, right? Instead, we have to rely on our concepts of elasticity, okay? Right, and so we're going to assume that we have linear elasticity, okay? And so what do we know about linear elasticity? We know that the stress in the truss is equal to E, the Young's modulus, multiplied by the strain. Okay. Okay. And so you can see here we have three elements in this equation. So we have the E. So we know E already. So the E is no surprise, and so we can kind of leave that alone. And so here we have the stress. Okay, that's our sigma, and then epsilon here is our strain. And so let's represent these using the variables from the problem here, or variables from this figure, and then we can kind of rearrange this as it's needed. Okay. And so let's do the stress first. That's it. And so we know the stress is nothing more than a force distributed over an area. Okay. Okay. In particular, we know that the force that's being applied for a structural stress like this is a stress on the cross section. Okay. Um, yes. Okay. Yeah. Yeah. So if you have questions on homework 4, I'll have some spare time at the end. Yeah. Okay. Where was I? Okay. Yeah. So we have the stress is the cross-sectional force over the cross-sectional area, and so we know that for this problem here. And so the stress in the cross-sectional force in this case is given by the tension T. Okay. And the cross-sectional area is the cross-sectional area of the truss, which is something that we know, right? And so that's one of the properties that we know about the truss element. So we're gonna have T divided by A. Okay. Okay. This is equal to next, we have the Young's modulus, and so the Young's modulus is already known. So I'm just going to bring that down. Okay, and now we need to represent the strain using the variables in the in the problem. Okay, all right. All right. So for a one-dimensional truss like this, we can say that the strain is equal to the change in length divided by its original length. Okay. And so the change in length here, we can represent that using the deformations at the ends. Okay. And so the deformations at the end, the difference will be d2 minus d1. Okay. Because if node 2 is being displaced to the right by amount d2, and d1 and node 1 is being displaced to the left by amount d1, okay, the difference in those deformations is the change in length of the entire element. Okay. And then of course, we have the length, which is another property that we already know about the truss element. So we can just leave out there. Okay. Okay. And so we have the following relationship. And so we have that T is equal to, T over A is equal to E times D minus D2 minus D1 divided by L. Okay. All right. So this is a good starting point here. And so we've taken kind of our usual kind of a stress-strain relationship for linear elasticity. And we've rearranged it to include, variables from the problem. Okay. Okay. So what I'm going to do here is I'm going to multiply both sides by a, and I'm going to pull L out of this fraction here. Okay. And so to do that, we get T is equal to AE divided by L times D2 minus D1. Okay. So this is good because if you kind of notice what I've done here is that, by multiplying both sides by A, on the left-hand side, I've gotten something with force, essentially. Okay. Right. What I've also done here is that I've isolated kind of the difference in the displacements here. Okay. Okay. This is starting to look like our spring element, right? And so if we look at our spring element, right, we use Hooke's law for that. Okay. We had kind of a similar thing. So we had force and displacement. Okay. And the thing that connected it was the spring constant. Okay. For a truss element, we don't have a spring constant because it's not a spring. What we have instead is this AE over L right here. Okay. And so, but you can see here that it kind of plays the same role as the spring constant. So this is kind of, I like to think of it as kind of like the effective spring constant of a truss bar, or truss element. Okay. All right, so let's roll with this. And so, if you remember from the beginning, we know that F1 is equal to minus T and F2 is equal to T. Okay. Let's go ahead and plug this in using this expression up there. Okay. So we know F1 is equal to minus T. So we say F1 is equal to minus AE over L times D2 minus D1. Okay. And then we have F2 is equal to T. So let's just plug in that entire expression up there. So F2 is equal to AE over L D2 minus D1. Okay. Let's take these two equations here, let's simplify them, and let's put them in matrix form. Okay. And so for the F1 equation, I'm going to distribute that negative inside, and so we have F1 is equal to AE over L times D1 minus D2. Okay. And then we have F2 is equal to AE over L times D2 minus D1. Okay. So let's go ahead and put this in matrix form. And so in matrix form, we have F1, F2 is equal to positive AE over L minus AE over L minus AE over L, positive AE over L times D1, D2. Okay. Just for the sake of simplicity, let me factor out AE over L because that's just a constant. And so, there's no need for it to show up in every entry there. So you have F1, F2 is equal to AE over L multiplied by 1 minus 1 minus 1, 1, D1, D2. Okay. Okay. And then this thing, or this matrix that kind of comes out of it, this is exactly our element stiffness matrix for a truss. All right. Any questions on how we obtain this here? Okay. All right. So let's do an example with this. And so this is going to be kind of a fairly simple example, but you'll kind of see this in action here. Okay. So I think kind of the nice thing about this example too is that it kind of shows you the entire kind of direct stiffness sequence. Um, and then just so you can see kind of every step from the assembly to the boundary conditions to the solution. Okay, so for this example, let's consider the following 3-bar assembly. Okay, okay. And so our assembly here will consist of three elements here. Okay, we have element A, element B, element C. Okay, and then connecting these elements, we have node 1, node 2, node 3, and node 4. Okay. Okay. We're going to apply a force, a horizontal force on node 2. Okay. So this force here is going to be 3,000 pounds. Okay. We have the lengths of each of the elements too. And so we're going to assume that element A here has a length of 30 inches. Element B also has a length of 30 inches. And element C also has a length of 30 inches. So they all have the same length. Okay. All right, let's list out their Young's moduli. Okay, so for element A, we have a Young's modulus of 30 times 10 to the 6 psi. Okay. We're going to assume that element B has the same Young's modulus, so 30 times 10 to the 6 psi. But then we're going to assume that element C here is made of a different material. And so its Young's modulus is going to be 15 times 10 to the 6 psi. Okay. Okay. And then finally, we have the cross-sectional areas for each element. And so for element A has a cross-sectional area of 1 inch squared. Okay. Element B is going to have a cross-section of 1 inch squared as well. Okay. So elements A and B are identical, okay, at least in terms of their properties. But element C is going to be much larger, and so element C is going to have a cross-sectional area of 4 inch square. Okay. Okay. So that's all the properties and all the stats for this problem. Okay. And so for the problem itself, what we want to compute, first of all, is we want to compute the displacements at all the nodes. Okay. The next thing we're going to compute, which we didn't do this for the springs, is we're going to compute the reaction forces at the end nodes. Okay. Okay. And so, whenever, and this is true just in general, whenever you have something constraining your geometry, usually for our case, it's going to be a fixed constraint. And so anytime you have a fixed constraint, the constraint itself needs to apply forces in order to keep the structure in equilibrium. Okay. And so we're going to compute what those reaction forces are based on our finite element solution. Okay. So that'll be kind of the new thing on this example. Okay. Any questions on any of this? Okay. All right. So let's go ahead and start. So let's go ahead and start our direct stiffness. You can think of it like an algorithm, but it's not really like an algorithm. It's more kind of a steps to do. Okay. Okay. So step one. So step one of the direct stiffness method is to label and discretize your geometry, which I've already done that for you. And so again, for most of the problems that we're going to do, the discretization and the labeling will be done for you ahead of time. Okay. Um, that means the next thing that we have to do is compute the element stiffness matrix for every element. Okay. Okay, so let's do that for each of the elements here. Okay. All right. So normally for these ones, where we don't just have a spring constant we're plugging in, we have to actually compute AE over L. I like to compute those ahead of time for the trusses because those get applied to every single element. Okay, so let's compute the product of AE over L for element A. Okay. Okay, so we know the cross-sectional area for element A is 1 inch square. Its Young's modulus is 30 times 10 to the 6 psi. And so if we divide that by the length, which is 30, we get a AE over L value of 10 to the 6 pounds per inch. Okay. That ends up kind of what being the unit for that one is. Okay. And so if we write out the element stiffness matrix for element A here, we have F1, F2, okay? Because we can see from the figure there that element A is connected to nodes 1 and 2, okay? Its value for AE over L is 10 to the 6, and so let's go ahead and put 10 to the 6 outside of the matrix. And then our matrix itself is going to be 1 minus 1 minus 1 1. And then that's going to be multiplied by its displacement vector d1 and d2. Okay. Okay. So pretty straightforward. And remember, the important thing for the element stiffness matrix is that you have to indicate which nodes that the element is connected to. Okay. Okay, so let's do the same thing for element B. So I'm going to go a little bit faster here just because it's mostly the same. Okay. All right, and so all the properties for element B are the same, and so its AE over L is going to be 10 to the 6 pound per inch. Okay. Okay. And so element B is connected to nodes 2 and 3, and so we're going to have F2, F3 is equal to 10 to the 6, 1 minus 1 minus 1, 1 times D2, D3. Okay. All right, and then finally we get to element C. So for element C, we're going to compute its AE over L. Okay. So its E in this case is is only 15 times 10 to the 6 psi. So it's half the Young's modulus of the other ones. Okay, but its area is 4 times as high. Okay, and so we take the product of E and A, and so that's going to be 60 times 10 to the 6 psi. We divide by its length, which is 30, and so in the end, what we get is 2 times 10 to the 6th pound per inch. Okay, that's its effective spring constant. Okay, and so its element stiffness matrix therefore is F3 F4 is equal to 2 times 10 to the 6th 1 minus 1 minus 1 1 times D3 D4. Okay. Okay. So those are all the element stiffness matrices from this problem. And so, the element stiffness matrix, it's probably the most time-consuming step. I think it's the step that people hate the most. Not because it's hard. It's essentially just glorified plug and chug. It's just that it's a lot to write down, and so you end up kind of spending more time writing down than actually doing stuff. And you'll see that once we kind of get to 2D problems, it's kind of very easy to kind of make a mistake at this point, just because on the surface it kind of seems like it's kind of a brain dead exercise, like you're just kind of filling things in a matrix. But that's kind of the time when you're most vulnerable to kind of make a mistake. And so you want to be kind of very careful in terms of how you place the entries in these matrices. Okay. Okay. All right. So that's step one, element stiffness matrices. All right. Step two is going to be assembly, and so let's go ahead and assemble our system here. Okay. And remember, the point of assembly is that now that we have each of the individual element stiffness matrices, we want to combine them together into one kind of global linear system so that we can solve it all at the same time. Okay, so F1, F2, F3, F4. Okay, so we have 4 nodes, and so our global stiffness matrix here is going to be a 4 by 4. Okay, let me go ahead and label all the columns here: F1, F2, F3, F4. D1, D2, D3, D4. All right, so those columns there should be D1 through D4, but it doesn't really matter. We're just labeling the columns. Okay. Okay. And so just like we did before, let's go ahead and highlight kind of the areas where we're going to plug in our elements. Okay. So let's start with element A. Okay. So we know element A is connected to nodes 1 and 2. Okay. And so that area of the global stiffness system is going to be here. Okay. Okay. Then we come to element B. Element B we know is nodes 2 and 3. Okay. So that's this part right here. Okay. And then finally we have element C. Element C is nodes 3 and 4. Okay. And so nodes 3 and 4 are going to be this kind of area right here. Okay. All right, and then everywhere we don't have any overlap, we're just going to put zeros there. Okay. Okay. And let me do this too, just to kind of make our lives a little bit easier, just so we're not, and this is something you can do too. It's not really a trick. It's just math, right? And so since we know that both of our element stiffness matrices have a factor of 10 to the 6, I'm just going to go ahead and factor that out. Okay. just to make our writing within the element stiffness matrix um, a lot easier. Okay, so let's go ahead and add in our entries here. So, in this case, we just kind of have our three boxes here that are all kind of contiguous, and so it should be fairly straightforward. Okay. Okay. So that is element A. Okay, so I put all ones there because, again, I factored out the 10 to the sixth out in front. Okay. Okay. Now we're going to do for element B. And remember, whenever you have boxes overlapping, you're just going to simply add those entries together. Okay. And so we have a positive 1 on the top left, -1, -1, and then a positive 1 on the bottom here. Okay. And then, we're going to add in the entries for element C. So we have a positive 2 in the top left, -2, -2, and then a positive 2 on the bottom right. Okay. Okay, so let me go ahead and simplify this. So whenever we have things added together, I'm just going to collapse them into 1. Okay. And so we have a 2 here and a 3 there. Okay. All right. Any questions on how we got this matrix here? All right, so that is the assembly. So next step is going to be our boundary conditions. Okay. Remember, when we apply boundary conditions, the way that we do that mathematically is that we use it to modify our global stiffness system. Okay, so we're going to modify the matrix that we have here. Okay. All right, so we actually have quite a few boundary conditions here. Okay, so let's actually kind of go back. Um, let's go back to the kind of original diagram here. Okay, sorry about that. I don't know what's going on. Okay, and so from original diagram here, you can see we have 3 boundary conditions. And so let me go ahead and circle them in purple here. Okay. And so first of all, we have the boundary condition node 1. So from this diagram here, we can see that node 1 is fixed to the wall. And so we have a fixed support on node 1. Okay. Very similarly, we have a fixed support on node 4. Okay. So fixed supports on node 1, fixed support on node 4. And then we also have a horizontal force being applied on node 2. Okay. Okay, so let's note all that down here. Okay, so those are our 2 fixed supports. And then finally, our third boundary condition was our external force of 3,000 pounds applied at node 2. Okay. All right, so let's go ahead and apply those to our matrix here. But normally what I would do is I would just kind of erase the entries here and add ones in. But we're actually going to use this matrix that we have here in the next step. And so I'm going to kind of rewrite the entire matrix down below with the boundary conditions factored in. Okay. Okay. So I've gone ahead and kind of rewritten our matrix here, just so that we have kind of a clean slate to work with. Okay. Okay. So let's go ahead and apply these boundary conditions one by one. So let's start with the fixed support. Okay. And so the fixed support on row one means that we're going to substitute our entire first row. Okay. Okay. And so if we substitute the entire first row, that means we're going to put a 1 on the diagonal entry. Okay, so that means we're going to put a 1 on the first entry because it's the first row. Okay. And we're going to have zeros everywhere else. And then on the left-hand side, we're going to put a 0 on that side as well because we're saying that displacement there is going to be 0. Okay. Okay. Next, we have the fixed support on node 4. And so just like in row 1, we're going to replace the last row here. Okay. And so just like in the first row, we're going to put a 1 on the diagonal entry. Okay. And so the diagonal entry for the fourth row is in the fourth column. Okay. So that's why I put a 1 in the bottom right. We're going to have zeros everywhere else on that row. And then we're going to have a 0 on the forcing vector on that side as well. Okay. So that applies the fixed support boundary condition on node 4. Okay. And then finally, we have the 3,000-pound force on node 2. Okay. And so that's going to be a load type boundary condition. And so the way that we deal with that is we just put that load directly into the vector there. Okay, so we're going to have a 3,000-pound force being applied on that. Okay. Okay. And then the last thing we need to do here is we need to plug in for F3. And since we don't have any fixed support on F3, we're not going to modify the matrix on the third row. And we don't have any force that's being applied on node 3 as well. Okay, so we're going to put a 0 here. And that 0 there is to represent that we have no external force being applied on node 3. Okay, and so that's it. And so now that we have the system in this format, we are ready to solve. Okay. And so the way that you can solve this system is, you can either plug it into your calculator if your calculator has that function, or if you're like me, where my graphing calculator has long been dead, you can go ahead and plug this into MATLAB. Okay. And so if we do that, we can get our solution for all of our displacement, nodal displacements here. Okay. Okay. And so we plug this into MATLAB. What we get is D1 is equal to 0 inches. D4 is also equal to 0 inches. Okay. So that makes sense because, that's where our fixed supports are. And so our fixed supports basically says that our displacements there is going to be 0. Okay. D2 here is going to be 0.0018 inches. Okay. And D3 is going to be 0.0006 inches. Okay. All right, and so that's the solution to our problem here. Right? Any questions on how we obtained this result here? Okay. All right, so that's part one of the problem. And so part one of the problem asks us to find the displacements at all the nodes on our system. Okay. The next thing it's asking us to do is to compute the reaction forces at all of the fixed supports. Okay. Okay. And so to compute reaction forces, we can take our finite element solution that we have just here, okay, and then we're basically gonna plug it back into our global stiffness system, okay. All right, but let's kind of visualize kind of exactly why that gives us the result that we want, okay. The reaction forces basically are, you can almost think of them as kind of like external forces that are being applied on your system, okay? Except they're not being applied, kind of conventionally, that we kind of, expect to find, that we usually kind of model as kind of an external force. These are external forces that are being applied explicitly at the supports to enforce equilibrium of our structure, okay? Right. So normally we don't, think about these as reaction forces, but they're there, right? And so, in order to kind of counteract kind of any other external force, these reaction forces have to exist in order to have equilibrium. Okay. And so the reason I'm kind of describing it like this is that essentially what we're solving for are the values for each of the nodal forces, F1, F2, F3, F4. Okay. Okay. And so in other words, we want to solve for the values for F1, F2, F3, and F4. In this case, we have four nodes, and so we have F1 through 4. That would be there in the absence of all the other boundary conditions. Okay, so this is kind of before we apply any of the other boundary conditions. Okay. All right. And so the way that you do this is it's actually quite simple. And so you're going to take your displacement solution or deformation solution. You're going to take your deformation solution that you found in the previous step. So that's D1, D2, D3, D4. Okay. And what you're going to do is you're going to multiply this vector by the original global stiffness matrix before you apply the boundary conditions. So right after assembly, before boundary conditions. Okay. So that's why, during this problem here, I kind of saved that original global stiffness system before we apply boundary conditions, because we're going to use it to compute the reaction forces. Okay. Okay, so let's kind of see what that would look like. And so if we look at our original system, So we have F1, F2, F3, F4, okay? So again, this is before any boundary conditions have been applied. So this is going to be equal to 10 to the 6 multiplied by 1 minus 1, 0, 0, minus 1, 2, minus 1, 0, 0, minus 1, 3, minus 2, 0, 0, minus 2, 2. Okay. Okay. And so if you kind of scroll back up in your notes, that's exactly kind of the global stiffness system before we applied the fixed supports, before we applied the external forcings and things like that. Okay. And then what you're going to multiply this by is your deformation solution. So your values for D1, D2, D3, and D4. Okay. And so you're going to multiply by a vector 0, 0.0018, 0.0006, and 0 inches. Okay. And so you're going to take this and you're going to perform the matrix vector multiplication. And of course, that's a lot easier to do in MATLAB or a calculator. And so definitely feel free to do that. Okay. All right. And so if you do that for this particular example, what you're going to get is the following results. Okay. And so we're going to get F1 is equal to minus 1,800 pounds. F2 is equal to 3,000 pounds. Okay. F3 is equal to 0. And F4 is equal to minus 1,200 pounds. Okay. All right, so a couple things here. And so, if you look at the values for, well, first of all, let's look at the values for F2, okay? And so for F2, we got exactly 3,000 pounds for F2. And so if you recall from our previous, from our original problem, that was exactly the amount of load that we were applying on node 2, right? And so if you did everything correctly, and so if everything works out, and you compute the reaction forces, you should be able to recreate any external loads that were being applied exactly. Okay, and so we got F2 is equal to 3,000, F3 is equal to 0, okay, because remember there's no load being applied on node 3, okay? So that checks out, that's good, okay? And then what we can see here, we get F1 is equal to minus 1,800, and F4 is equal to minus 1,200, okay? And so if you add those together, you can see that you get minus 3,000, and then if you add minus 3,000 to positive 3,000, we get a net force of 0, okay? And so ideally, you should get kind of everything canceling out, which as it should because you have a static situation. Okay. Okay. Any questions on this? Okay. All right. And so that's reaction force. And so reaction force is not too big a deal. Okay. All right, so the last thing I wanted to cover today before we close it up is expanding these results to 2D. Okay. Okay. All right. So far, all of the direct stiffness problems that we've done, either involving springs or involving trusses, have been 1D problems, right? And so the deformation is only in one dimension. So we either have tension or compression. Okay. But that's very limiting because there are some there are some situations in reality that can be modeled with 1D results, but the vast majority are multi-dimensional. Okay, in particular 3D, but before we get to 3D, we have to get to 2D. Okay, and so we can and so the next step is to see how can we extend our results here for spring and truss element stiffness matrices to 2D. Okay. 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 And so making the jump from 1D to 2D is actually quite a bit of work. And so we're going to focus mostly on 2D in this class. We're not going to go to 3D because going to 3D is kind of a more busy work than it's actually worth. But I think more importantly, going from 2D to 3D doesn't introduce that many new concepts, but going from 1D to 2D does. Okay. Okay. So let's start. Um, And so let's start by noting that the element stiffness matrices that we've defined so far kind of assume a one-dimensional system. Okay. Okay. And so it basically assumes that the deformation, or at least the way that we define the deformation, is going to take place, in the along the axis of the truss element. Okay. Okay. But in 2D, okay, in 2D, what can happen is that our elements may be oriented in an arbitrary direction. So they may be rotated up from its usual orientation. Okay. And so, for example, let's say that we have a truss element, right? Everything we've done so far is that we've kind of assumed that the truss element is kind of laying flat. Okay. But we may have situations where we have an element that has to go like this. Okay. And so, mechanistically, we're still going to assume that the truss elements are following the same behavior. Okay. And so we're assumed that it's only going to, expand and contract, right? And so it's either going to be tension or compression. Okay. It's just that when the elements are rotated, expansion or tension and compression are in slightly different directions. Okay. Okay. In particular, okay, even though we have our truss element here that's kind of rotated up, and in fact, let me give you an angle here. Okay. Let's say that we know the angle of rotation. So we know that the angle is element is rotated up by that angle. Okay. We know that its displacement is going to go up and down the length here. Okay. But the problem is, that orientation may not be consistent with our usual coordinate system. Okay. And so let's say that our usual XY coordinate system is kind of as it normally is. So we have the positive X direction going, horizontally, the positive Y direction going vertically. Okay. And so that means that we can represent any kind of tension and compression of the truss element in its components in its original coordinate in the kind of what I call kind of the original stationary coordinate system. Okay. Okay. And so in the blue arrows here, so let's say that in the black there, I have D1. Okay. So D1 is a vector that's kind of pointing up to the right. Okay. Because it's kind of an arbitrary vector, we can break it up into components. So we have D1x, D1y, okay, which are the x and y components respectively of our original D1. Okay. All right. And so this kind of implies, maybe the way that we can tackle this is that, we already have an element stiffness matrix, if we assume that all of our deformations are going to be within the same axis in the same direction. Okay. But if our elements are going to be rotated, then we need to kind of adjust this. Okay. And so what this kind of implies is that maybe we should be working in multiple frames of reference, okay, or multiple coordinate systems. Okay. And so let me go ahead and give you a couple definitions here. Okay. And so let me first define the local coordinate system, okay, or the local reference frame. And so both are kind of synonymous, or at least I use them synonymously. Okay. And so the local coordinate system, this is a coordinate system that's attached to a particular element and rotates as the elements rotate as well. Okay. Okay. And so this is important because in the local coordinate system, the local x direction always points down the axis of your truss element. Okay. Okay. So that's the local coordinate system. I'll draw a picture to kind of illustrate this in a second, but let me define the second coordinate system that we're going to be working with, which I call the stationary coordinate system. And so the stationary coordinate system, kind of like its name applies, is stationary. And so it's not going to move. And in fact, it's going to act as kind of our global kind of point of reference from which we're going to perform our rotations from. Okay. And so usually, usually for most problems, our stationary coordinate system is just going to be standard x and standard y. So standard x is just going to be kind of perfectly horizontal, and standard y is going to be perfectly vertical. Okay. Okay. Okay, so let me draw a figure here to kind of illustrate kind of what I mean. Okay. Okay. And so let me draw kind of a stationary coordinate system first. Okay. Okay, so this is kind of our usual stationary coordinate system. And so it's just kind of our standard x, standard y. Okay. And so a local coordinate system is, let's say that we have an element or a truss element that's kind of rotated upwards by a certain angle. Okay. And so what that's going to do is that it's going to take its local coordinate system and rotate along with it. Okay. So let's say that we have kind of an element that's kind of rotated in this direction. Okay. And so we'll call this x hat. Okay. And that's going to rotate the y direction as well. So we're going to have a standard y hat in that direction too. Okay. Where the orientation of this new coordinate system is given by an angle theta, where that angle theta represents how much our local coordinate system has rotated away from our stationary coordinate system. Okay. And so that's how we kind of define between the two coordinate systems. Okay. Okay. So this is important, because first of all, because of the way that we've defined the element stiffness matrices, what we can say is that in a coordinate system local to that element, we can use the exact same element stiffness matrix that we had before. Okay. But if we want to take that element and have it interact with another element that may be in a different orientation, okay, we need to make sure that those two are kind of meeting in the middle. Okay. And so in other words, we compute their element stiffness matrices not relative to its own local coordinate system, but relative to the stationary coordinate system. Okay. And so, in other words, the way to kind of summarize that is, we want to compute all element stiffness matrices relative to the stationary coordinate system, so we can assemble them all together. Okay. Okay. And so what we're going to see on Thursday is basically, based on their relative orientations, we're going to define what's called a rotation matrix. And so that rotation matrix will basically take any vector in one coordinate system and transform it into a vector in a different coordinate system. Okay. Okay. So one last thing, I want to mention before we go. Okay. And so, when we're talking about kind of different coordinate systems and rotations and all these things, I know it's very easy to kind of, get lost in the sauce. And so there's a lot of details, there's kind of a lot of concepts. And so, it's a lot. And so, and I think it can kind of be intimidating to some people. Okay. And so, when we're talking about different coordinate systems, different frames of reference, just think of them as kind of different ways of looking at the same things. Okay, because underneath all these different coordinate systems and perspectives, our truss elements are still going to be the same, right? And so it's still the same structure, right? And so no matter which direction you look, at the CS building, right? And so if you stand outside the CS building, whether you look at it from the 57 freeway or whether you look at it from the quad, right? It's still the same CS building. It's still the same old decrepit building that, ironically is earthquake safe, but it's still kind of an old building that needs to be updated. But the school can't find the money to update this old building, right? It's still the same building. And so, I want you guys to think about these coordinate systems in kind of the same way, right? Our elements and our vectors and displacements and everything, it's still the same. It's just that the way that you define them is slightly different, or the way that you kind of or I should say, maybe the better way to say it, the way that you describe them is slightly different. Okay. And so, if we take our two coordinate systems here, okay, and I draw a vector, right? So this vector, and I did my best to kind of make them the same. This vector U is the same in both reference frames, right? So they're identical. But if you were to represent this in the stationary coordinate system, right, you'd have ux and uy, right? Those would be its components, where ux, okay, ux would be kind of the distance along this, or you can think of it as kind of the projection of this vector down onto the x-axis, okay? And uy would be the projection of that vector onto the y-axis, okay? If you take the same u vector, so exactly the same vector, so in the exact same orientation, the exact same length, but if you defined it relative to the local coordinate system, it would have different components. And so you would have ux hat, uy hat, okay? Where ux hat will be the distance along kind of the x hat axis along which the vector acts. Okay. And uy hat would be kind of the projection along the vertical axis, or the local vertical axis that acts. Okay, so same vector, it's just you're describing it in different ways. Okay, and so that's kind of the mentality that we're going to work with on Thursday when we kind of pick this up again, and we kind of write down kind of the rotated version of our element stiffness matrix. Okay. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all we got planned for today. So I know at least one of you have questions on activity 4, so I'll go ahead and stick around for that. Question in the chat, so when do we have the midterm exam for this class? And so the midterm exam for this class, I'm planning for it to be the Thursday right before Thanksgiving. So it's going to be the last class that we have before we leave for the Thanksgiving break. Yep. Did I miss any announcements in the beginning? No, there was no announcements in the beginning. Just continue working on activity 4 and continue working on the midterm project. Yeah. Mm-hmm. All right, so thank you guys for coming. I'll stick around for a few minutes to answer some questions on activity 4. But if you don't have questions, then I will see you guys on Thursday. All right, MJ, I see that your mic is on, but I can't hear you. Oh,
Can you hear me?
Yep, I can hear you.
Yeah, so for homework 4, I finish up to problem 5.
Okay.
I don't know how to start problem 6.
Okay, let me take a look. Problem 6.
6 and 7. I think we change it to shell from solid. So we making up again with solid on the 7.
Yeah. Mm-hmm.
But fortunately, I don't know how to start for problem 6.
So for problem 6, I want you to change the support condition. And so kind of in the default configuration, we applied a a fixed support on one side of the road and a displacement support on the other side. If you kind of follow the the PDF exactly. And so I want you to add basically additional supports. And so instead of supporting it from the ends of the road, for example, for in the PDF there. So let me go ahead and share my screen so you can see. Okay. And so this in this PDF right here, you can see that instead of applying the supports here, right? I've applied fixed supports at each of these dots right here. Okay. And so all I want you to do in problem 6 is just change the fixed support to something different, so that you get a different result. That's all problem 6. Okay.
Okay. And then so it has to match with problem 5, which I made individually like the changeable mesh. And then just because the problem 5 has a many iterations, so problem 6 only need to one, right?
Yes, yeah. So problem 6, you only need to do it once. Yeah. And then for problems, you have more questions on problem 6?
Oh no, I think that's all good. But problem 7, yeah. Can you
Okay. So for problem 7, I basically want you to try to do the analysis using solid elements. And so I think the best way to do this would be to start a new project and just kind of reload the geometry, but don't convert anything to shells or beams. Just try to run it just straight up as it is. And so one or two things can happen in problem 7, and it kind of depends on your computer. Either you succeed and you're able to mesh it and you're able to get a simulation out of it. And what you're going to find is that your solution is going to be very, very different than what you saw with the shells and beams. Or the other thing that might happen is that you just may not be able to run a simulation at all. And so it's either going to fail in the meshing, or maybe it succeeds in the meshing, but the mesh is so kind of poorly conditioned that it's not able to run a solution. And so all you get is errors. Okay. And so both are fine. And so the point of problem 7 is to kind of illustrate that, if you were to take a geometry like this and try to do it with solid elements, where for geometry which has a lot of thin and slender geometries here, it's very ill suited to use solid elements here. You're going to struggle a lot. And so you're either going to struggle in terms of, it's sometimes for some people it's impossible to even get a solution, or you may struggle with the fact that the solution that you do get is just wrong, or just really off from what it was before. So just try your best with problem 7. Don't spend too much time on it. Just try to mesh it with the solid elements. If it works, it works. If it doesn't work, then don't worry about it. Just say that you tried meshing with the solid elements, it didn't work, and here's the error that I found. And so I expect that to be the case for most people, actually.
Okay, because in my thought, we change solid to shells, which is less area. And if you change it back to solid, then we're gonna have a more number of elements.
Well, so remember, so if you're meshing a three-dimensional object, you're not using shell elements anymore. So you're using solid elements.
Solid, yeah.
And so the elements themselves will be much bigger, because they're going to be hexahedrons or tetrahedrons, as opposed to shells, which are in this case are just quadrilaterals, right? And so it's very possible to end up with much more elements, especially if you use a much smaller mesh size. But remember, the whole important thing is that whenever you're meshing thin geometries, you want to have multiple elements through the thickness, right? So that's kind of what we discussed, when we first introduced shell elements.
Yeah.
Okay. And so what you're going to see is that even if you are able to mesh it with solid elements, your mesh is going to look something like this. And so it's going to have only one element through the thickness. Right. So it's not going to be a very accurate simulation. Yeah.
Yeah, got it. Thank you.
Okay. All right. Any other questions on that?
Hi, Professor.
Yep.
So from your explanation, can I conclude that I don't need to figure out the error. I just if I have the error, I just move on with the error.
Exactly. Yeah. So you don't need to fix the error. So if you're getting an error with the meshing for the solid elements, just put in the PDF, or just put in your answers that you ran into an error, and just show me what that error is, and then that's it. And so it's supposed to be you either fail and you get an error and you can't fix it, and that's fine, or you get a simulation result and it's really bad. And so you're not supposed to succeed at problem 7. That's the
Yeah,
that was the point of that.
yeah. Another thing is that about problem number 5, when I was doing the iteration, I I've I noticed that, like, for example, like when I from like when I put the size element 1 inch, like I got like a stress of 11,000, but when I put it like 0.3, it went up to 70,000. Um, so does it mean that it's because based on my understand that the smaller these element size, the more accurate, right?
Yes.
So like in this situation, like what you see the big difference, like 60,000. So in this for, like, let's say for the future, it's always better to just to try to use a very small element size, right?
Yeah, so I mean, you
Because
want to use as small an element size as you can, where your simulation is still going to be practical, and so it's still going to be able to run in a practical amount of time. And so, but what can happen sometimes, and we'll talk about this kind of later on in the class once we get to kind of some more advanced topics, is that sometimes
yeah,
if you refine the mesh too much, then you could get kind of stress concentration at certain areas. And so in particular, if you have areas with a lot of kind of sharp corners, and so if you kind of
yeah,
mesh, and so what can happen is that if you mesh that too much, then what you're going to see is that the stress is never going to converge. It's just going to keep going up and up and up and up and up and up.
yeah.
And so
Okay.
you need to be a little bit careful in those areas. And so if you're seeing that, your stress just keeps kind of exploding as you refine the mesh,
Yeah.
what you actually need to do is you need to actually go in and kind of smooth those corners out. And so normally you would probably go back into SolidWorks and with the part and maybe smooth out those corners so that you don't get that stress concentration. So that's a separate issue. And so that's not an accuracy issue. That's kind of like a stress
Oh.
amplification issue. Yeah.
Okay, okay, okay.
Yeah, but normally yes, you'd want to keep it, you want to keep refining the mesh, but the stress
Uh,
shouldn't blow up that quickly. And so you should see differences as you refine the mesh. And so you should see
yeah,
the stress change. But if you see it blow up like crazy, then that's probably you
yeah.
probably have stress amplification somewhere in your model, and you have to kind of smooth those corners out.
Okay, so you adjust the geometry, just
Yes.
change the
Yeah.
application. Okay.
So for this,
Yeah.
I mean, for this activity, there's nothing you can do about it because I provided you the geometry, but that's kind of what you would do in practice, if you're when you're applying this in in the real world.
Yeah. Okay. Thank you so much for your time. Have a good
Yep.
night.
All right. Any other questions? Okay. All right. I'll see you. Oh, Edward, you have a
Professor,
question?
yeah,
Yeah.
sorry about that. So I believe I got to like around problem 3. Well, when it came to getting the solution, and I ran into like 3 separate warnings.
Okay.
It was a solver pivot warnings or errors have been encountered during the solution. This is usually a result of ill-conditioned matrix, possibly due to unreasonable material properties and under constrained model.
Mhm.
Would I just have to go back to the space claim and essentially redo that whole part?
So usually the solver pivot warnings are due to either it can be 2 things usually. So either you have an under constrained model, and so you don't have enough fixed supports to kind of fully constrain it. So you basically have rigid body motion, um, which is not that common because usually people are pretty good with adding their fixed supports. The other way that error can occur is through the connections, and so I would actually double check your connections between the parts and make sure that you're bonding the right parts together. And so it could be that you're either missing a bond or you're kind of misclick on a certain part where one part is not being bonded properly. And so when you apply the force, again, you have a part that just there's nothing supporting it, and so it just kind of falls through to the to the abyss. Yeah.
Okay then. All right then.
Yeah.
So I'll most likely just go through all of that again, double check it, and just make sure that that's essentially it.
Right. Yeah. So double check the connections. I think the most common error was that when you're making connections between like the road and the bridge or something like that, you want to make sure you get the edge of the road. And so I've seen people kind of connect, when they click on the road, they end up accidentally clicking on the entire road surface itself. And so you want to make sure you click on just the edge and just mate that to the bridge. And then same thing for the beams too. Make sure you click on each individual beam and then mate that to the road. And so yeah, those are probably the two most common things that can occur. Yeah.
Wait, for the beams, would I be clicking the vertices on the edge, or would I be clicking the actual beam?
So when you're mating the beams to the road, you want the actual beam itself.
Okay.
But when you're mating the beams to the sides of the bridge, those are just the endpoints. Yeah.
Okay then. All right then. Well, that was it essentially. Thank you.
Okay. Yep. No problem.
All right then. Have a
All
good
right. Good
one.
night. You too.